So the last topic for today is graphs of polynomials. So we're going to continue talking about graphs throughout this course, but it's good to make sure that we understand how to think about graphs of polynomials. So we're already familiar with f of x equals x squared and x cubed, just because we've talked about those a little bit throughout this course already. But we want to talk about what happens with larger powers of x. So if we generalize to y equals x to the n. Well, if n is even, so say we have y equals x to the fourth, it's actually going to look a lot like a quadratic, except, you might tell by my picture or from the supplemental notes in the textbook that the graph is a little bit flatter on the bottom. It's going to get more and more square shaped on the bottom, and it's going to become narrower at the top. But overall, it's doing the same thing, right? It's going through 0, 0, and we're going up on either side. When n is odd, so say we have y equals x to the fifth, we still have that flattening. It's getting more and more square-like towards the x-axis, but we're getting narrower as we go off to infinity and negative infinity. So we also might notice that the even powered ones are going to be symmetric, right, which we've also talked about, right? These are even functions, and these are going to be symmetric on the y-axis. And here we have symmetric about the origin. So that means we're rotating it 180 degrees to get the other part. Okay, so both of these examples have x equals 0 as the only x-intercept. They only cross at x equals 0, and that's because if I set a power of x to 0, the only time this is going to happen is if I have 0 to the nth power, which is 0. So only when x equals 0 am I going to cross the x-axis. So we want to talk about what happens when we have other x-intercepts. So say we have this function, x plus 1 times x minus 2 squared. If we set this equal to 0, then that means x plus 1 equals 0, or x minus 2 has to equal 0. Right? So either x equals negative 1 or x equals 2. So on the graph here, we can see that. At negative 1, we're at 0, and at 2, we're at 0. And overall, this function is degree 3, because this factor has a power of x, and here, this power is actually 2. Power of x is 2. So overall, we have degree 3. So we know it's going to go off to infinity to the right, and it's going to go to negative infinity to the left, right? So just like the picture here. Now, we also might notice that at negative 1, we're passing through the x-axis. We're going through, right? But at 2, we're going down, and then we're kind of bouncing off of the x-axis. So there's something about that that actually can be generalized. And I have the rule written here, but really what we need to look at in our previous example is that x plus 1 is to the first power, and x minus 2 is to the second power. So whenever we have a multiplicity, that's what it's called. Multiplicity is the power of that factor. If the multiplicity is even, then f of x bounces at b comma 0 if our root is at b. So here we have an even multiplicity at x equals 2. Right? So at 2, we're noticing this bouncing behavior. But if n is odd, then f of x crosses the x-axis at that place. So here, our multiplicity was odd, it was 1, And so at x equals -1, we're actually passing through. We're going across the x-axis. All right, so we're just going to do a simple example of this with another function, just to get the idea of what's happening at the x-axis for this function. So in the previous example, we already had it factored. So in this one, we need to factor first. So we always need to factor so that we can figure out what our intercepts are. So I notice that I can take out an x cubed from everything, and I'm left with an x cubed plus 2x squared minus 4x minus 8. And now on the inside I have 4 terms, so I'm going to factor by grouping. I'm going to see if I can do that. So from the first 2, I'm going to take out an x squared, and I'm left with x plus 2. And from the second 2, I'm going to take out a minus 4, and I'm left with x plus 2. So it looks like I can take out not only an x cubed, but an x plus 2, and I'm left with x squared minus 4. Well, we know how to factor that. That's a difference of squares. So our final factorization is x cubed times x plus 2 times x plus 2 times x minus 2. Well, it looks like we have 2x plus 2 factors, so I could actually write this as x plus 2 squared times x minus 2. So now we have to think about multiplicities of each root. So here, if this is equal to 0, then I could have x equals 0. I'm going to write this over here. So I can have x equals 0, x equals -2, or x equals 2. Now the multiplicities of each, well, for 0, I have a power of 3, so the multiplicity is 3. For -2, I have a multiplicity of 2. And for x minus 2, I just have a 1. I just have one of those. So this is 1. So we have odd, even, and odd. Okay. And my overall degree of my function is defined by my leading term, right? So x to the 6th power, which is even, right? And since we have a positive 1 in front, we know that it's going to be going up on both sides, as opposed to going up on the right and down on the left. So we know my end behavior, right, what's happening at the ends of my function. And I know I cross at x equals 0, at -2, and at +2. So we can get an idea of what's happening here. All right. I know that I'm going to pass through at 0, right? I'm going to bounce at -2. So since I know I'm coming from up here, I have to go down and bounce, and then go back down through x equals 0. And then I also have to go through x equals 2 and rejoin up here. So this is a sketch, meaning that it's not perfect, and I haven't actually calculated anything. All I did was figure out where I crossed the x-axis, and it's given me a shape, right? It's just given me a shape. Now to make our sketch even more accurate, I could figure out, what f of 1 is, right? It turns out to be a lot lower, so really my graph would look, maybe something like this. And here Maybe it's a little bit more, but I think it's pretty accurate like this. So at that point, we're just improving our sketch, but really what I want to make sense of is what's happening at these x-intercepts.